Hi, good morning, everyone. I think we have enough people to get us started for today. So this is May 24th session of Earthquake Engineering course in the University of Victoria. I am seeing that we are getting close to 20 people. Normally in 5 minutes, a few more people will show up. So that's totally fine. This is the outline of the course that I'm sharing here. We are now finished with module number 1, and we are going to start discussing module number 2, which is multiple degrees of freedom systems. We will get into that today, start that today, and we go as far as we can in 1 hour and about 15 minutes or 1 hour, 20 minutes. I should also remind you, I think you guys are aware of the deadline that we have today for draft work plan. And it's basically end of today. I think Armando set it to 1 minute before night. Please do, and please submit it in the bright space. It's easier for all of us to like see it in bright space. I received a warning that my internet is slow. It shouldn't be, so maybe it was just momentarily. If there are issues, let me know, and maybe I can use my cell phone internet if my Wi-Fi is causing issues. But I think everything is working. Yeah, there was an email asking about how perfect the draft work plan should be, and I responded that please explain in the clearest words and paragraphs what you want to do. It's good for you. It's most importantly good for you. Like the more clear you are on what you want to do, the easier life you will have in the next month or two when you want to complete the task. So just think about yourself. Explain it in clear words to yourself and your team what you want to do, and then how many hours you want to spend. If you are clear to yourself, then definitely you get the full mark. And this is only a draft work plan. You see it has 10 marks. However, you will have another opportunity in about 2 weeks to improve your write-up and make it even better and submit one more time. So just, use your own judgment, upload your draft work plan, which you think is okay. This is not final. Behnam and I, we try to give you some comments, maybe general comments to everyone and specific comments to some teams if we think it's like too light or too much work, etc. We try to really find that out so that no team is working too hard or too little, both of them. And then on June 7, end of June 7, you can resubmit your work plan. June 7 is basically the day that we will have a class on campus showing that shaking table that UVic owns, and we will do a few tests on that shaking table. And the Tuesday of the same week, there is no class, and the class on 7 June is in person and for about 3 hours or maybe 10 minutes less. So be prepared for that. I will inform you which classroom you should come in. And I expect that everybody, all the class, show up in that session, for that session. Hopefully, I think it's not I know that's probably not the most difficult assignment for your engineering life or learning engineering live. So you will submit this by end of today, and you will have an opportunity to even improve it in the next 2 weeks. So stick to the deadlines. There is some score for remaining in the deadline, and so if you are late, you may lose points in a way. And again, this is good for us and good for you, as you will feel better when you have your work plan. Question from Hoichi. For the work plan, one of the members submit for the whole group, or everyone need to submit? No, one submitter. Yeah, I don't exactly know how the system works. Probably Armando has created one submittal location for the team. If there are individual ones, yeah, please only submit one time so that there is no confusion. Everybody's name would be on that work plan report in a way, and we will know who is involved. Another question from Japjot. Will we receive feedback grades for our draft work plan before the... Yeah, exactly. That's the plan. The plan is that Bernam and I go through those work plans quickly, both give high-level comments, meaning that do more, do less, this is too much, too little, and also a little bit into the paragraphs and the write-up and other stuff. Then you will have a nice final work plan in 2 weeks, which is beneficial to your team. So the answer is yes, you will receive feedback. Okay, so did I answer the questions? If you guys feel that you are in good shape to catch up with the work plan, we can move on. Here on the right space, I see that we have 7 groups, which is fine. 30 people. I think the total number of students, learners is 30 people. It's like 17 to 21. Yeah, exactly 30. So all 30 people, 30 learners have found their team, which is very nice. And 3 teams have 5 members, which is okay. It's acceptable, but I will more carefully look at the work plan for those 3 teams so that make sure that they have accepted slightly more tasks. It's like 25% more tasks than a team with 4 members. So we need the teams with 5 members show more task, more commitment in a way, because there are 5 people. That's the only restriction. Otherwise, totally fine, and they can have a good grade with 5 people. Now, I think this is final, 7 teams. So I will edit the work plan. Only the part of it where, like for presentations, we had 2 days of presentations. You see 26 July and 2 August. I was kind of estimating 9 teams. I was expecting even more learners based on last year experience. But yeah, we have 30 people, which is a very good number. And 7 teams, which is again a good number of teams. So no, I'm not complaining. So in a way, it's good. So I will edit this, maybe 4 teams in one day and 3 teams another day, and we can have maybe if it finishes too fast, we can have more discussions or extend one of these previous modules into those 2 days. These 2 days, again, mark your calendar. 26 July and 2 August are Fridays, and the class will be on UVic campus. I will be there, and Benham would be there, and like everybody should attend both sessions. Must attend both sessions. Okay, that's it. A reminder of deadlines, etc., which I think is smooth for you guys. Now I can switch to discussion for today, which is we are starting the second module of this course, which is multi-degree of freedom dynamics. One more time, I remind everybody that this has been maybe historically in the past few years before even I take over, it has been a very extensive course in a way. And so we cover a lot of, like each module could even be one graduate course by itself. And as a result, we try to keep it high level so that you are familiar with terminology and what is important in dynamics of structures and in earthquake engineering. But the intention is not to go too far into details, which you will do maybe in work or if you go to grad school, etc. You will dive deeper. You can dive deeper into each one of these modules. And that's the second reason why I was not considering a, say, final exam, because I think this is a little bit too heavy. Maybe if you want to have an exam, you should have it open book and then open book exams, because like invigilating them should be difficult. So there are a lot of substance in here and it's difficult to memorize all of them or go to exam having everything in your memory. But please attend the classes, do your best to learn very high level and use what you learned in your projects. And you will be happy. You will be happy that you took this course. Jumping back into the physics of the problem, the physics of the problem, I try to show on a sketch on the right-hand side. We can make this a little bit wider. Yeah. So there's this sketch on the right-hand side, which kind of introduces the physics of what we are studying. Say for us, structural engineering and structural engineers, we always assume that we will be in charge of analysis and design of buildings. And although I don't right now, and so the typical building, two-story building, multiple-story building could be a potential multi-degree of freedom system in terms of dynamics, because we have masses mostly concentrated at the floor. And as soon as you have a two-story building, you have two floors, which move pretty much independent from each other. So you have a 2 degree of freedom system responding to your earthquake excitation, which is at the base. And as we previously shown for single degree of freedom system, although physically the source of the loading is base excitation, but equivalently, this is not even a simplification. Equivalently, we can assume that there is a variable load applied to each mass. And mass, the location of the mass is basically the your dynamic degrees of freedom. This system might have other degrees of freedom as well. We will discuss that, but the dynamic ones are important to us. And in a dynamic analysis, earthquake analysis, you are concerned with 2 degrees of freedom, which are lateral movement of the first floor and lateral movement of the second floor, U1 and U2, which are pretty much independent from each other. We cannot merge them into 1 degree of freedom. The system has mass, as I discussed, and there is damping. which is important in the system. Damping in the source that I use, probably Chopra, was shown with this sign. So this is not bracing, this is damping. Damping just indication of damping schematic showing schematic showing damping. And so the it's not bracing, and the damping is in a way hidden in all the members. All the structural members have their own damping, so it's not as if you have damping. The whole system has damping, and schematically is shown as C2 for second floor and C1 for the first floor. Another important physical phenomena, in a way, physical description of the system is its stiffness. And each floor has its own stiffness. Say we have the stiffness of the first floor resulting from in the system shown. Apparently, the source of stiffness is mostly columns, and the way it's illustrated, the flow are very rigid. So it's like they are in a way source of stiffness because they are very stiff, extremely stiff. But in terms of the solution, we are concerned with level of stiffness of the columns because the beams or the flooring system is shown to have extreme rigidity, which is the case in most buildings, especially if they have like concrete slabs or very rigid wooden slabs. The flooring system could be considered very rigid. And we will have some discussion about those issues when we are discussing the module on concrete and wood. All right. One more person is joining us. No name, but that's fine. So I just discussed the physics of the problem. Like in engineering or in physics, we try to use mathematical models for a physical phenomena that we observe in a way. And we have multiple level of complexity. We normally, I mean, I will discuss this a little bit further, maybe in a couple of weeks, that we normally consider multiple different levels of complexity. And accuracy, we want to have good high-level estimates, and sometimes we need very detailed mathematical modeling and numerical modeling. So this is an exercise in creating the math model for this phenomenon. For single degree of freedom, we already discussed that, how we arrive at this equation, partial differential equation. Multiple degree of freedom is parallel. So in parallel, you can assume that instead of having single values, you have matrix values of mass because you have more than one mass, and more than the vector value of acceleration because you have more than one acceleration. This bold presentation, like I have used bold A versus non-bold A. The bold normally emphasizes and indicates basically vector value versus scalar value. And acceleration is a second derivative of displacement. So the second equation for multiple degrees of freedom basically is an equation. We can consider that a sophisticated equation which has one variable, which is u, and we can solve for displacement. We will try to find different methodologies like in different levels of complexity in a way, very complex, it's very simple to obtain, to calculate U for the forcing function. And we previously said that the forcing, even when you have base excitation, it's equivalent to having a forcing function. Moving forward. So now I talked about matrices. Normally the mass matrix is diagonal. For multiple degrees of freedom, you have a diagonal mass matrix, which each one of these, like for your previous system, they were M1 and M2. So a diagonal mass matrix there. Jumping to a stiffness matrix, you guys might have, or I mean, last year some people were telling me that it's same time, like the same summertime that they were taking earthquake engineering, they were also taking a course on structural analysis, and where you get more familiar with this stiffness matrix, which is symmetric and shows the relation between forces on the system and the deflections in the system. And damping matrix is also symmetric. It's new, so we'll discuss it a little bit further. It indicates the relation between velocity and force. So when your system has certain level of velocity, it resists movement because of damping. So damping and velocity causes resistance, stiffness, and deflection. Obviously, we know that structural engineering is more about relation between force and stiffness, so we are most familiar with that. And this is the inertia term, how the masses in your system accelerate, and they also cause resistance. So which is, we can normally call it inertia, inertial resistance. Again, earthquake excitation, trying to arrive at that equation again. We have a system which has a total acceleration, meaning moving of the masses with respect to a reference point which is completely silent. And there are velocities and there are deflection. That's what really happens in the earthquake when you have base excitation. We have shown U of ground at the base. However, we are not really too much interested in the ground movement. We are mostly interested in the relative movements, which is U. And that relative movement causes damping forces and causes stiffness forces. But it's the total acceleration which causes inertia forces. We divide this term into two parts. One part is the relative movement, and one part is the movement of the ground, multiplied by some influence vector, which basically, in mathematical term, the influence vector tells which nodes are attached to the ground, because we have a big system of many nodes, and the influence vector just dictates which nodes and in which directions or which degrees of freedom are connected to the ground. That's all it is about the influence vector. And similar to what we did in 1 degree of freedom system, so here's the typo. So I was trying to separate, like I wanted to insert ut into this above equation. Therefore, this is not total anymore. So you have the relative acceleration, relative velocity, and the relative displacement. and the ground acceleration goes to the right-hand side. So I can fix that. You always find typos. And practically, we will have a forcing function, P effective, which is the term on the right-hand side. And on the left-hand side, we only have relative u. So this t should be crossed out. So this t shouldn't be there. I will fix that and upload it one more time to the bright side. So the same trick or mathematical solution, just to get rid of this total acceleration and have relative u on one side and forcing function on the other side. Yeah, I have repeated the same thing, but so the term on the left, all the terms on the left side are relative movement, and there's no total movement. So page 5 and page 6, I should fix this. So that's the outcome. However, in this slide, we wanted to focus on elastic properties. Sometimes the relation between movement and force is inelastic, like if we have inelastic material. Just to create a contrast, here we had elastic material where we have a linear relation between stiffness forces and deflections. Here we have nonlinear material such as yielding material, etc., where this relation is nonlinear. So this partial deflection differential equation, this PDE, becomes even more sophisticated in a way, and numerical methods become even more important to solve this problem, this math problem. So I think it's very important that you know high level what we are dealing with before we move on to easier solutions that are provided for us engineers. There are some researchers, or there have been many great researchers who have created simplified solutions for engineers like myself so that we more quickly can get to the results and more quickly verify the results. The sophisticated solutions, they have two issues. One is that they are difficult to complete the solution, but even more importantly, they are more difficult to verify. Like one smart person completes a solution, but how can I know that he didn't make a mistake? So, or she. Therefore, yeah, so the simple solutions have a two-edged benefit. They are easier to implement, they are easier for verification. They become even more important for verifications. Nowadays, there is a lot of more and more interest in sophisticated solutions, such as complicated finite element tools, but we need to verify them, and the easier solutions are there to help us with verification. So basically, what we discussed right now was that there is a forcing function, which is equivalent of base excitation, and that forcing function is equivalent to or goes into forces caused by deflection, which are like the stiffness type of forces caused by velocity, which are more like damping type of forces, and forces caused by acceleration, which are more inertial type of forces. What is degrees of freedom? People who have taken courses on analysis of a structure, they know that normally in 3D, we assume 6 degrees of freedom per node, 3 displacements in each direction, and 3 rotations in each direction. So the degrees of freedom easily add up to 6 per node. Here we are showing a 2D problem, so we are not interested in out-of-plane movements or rotations. Therefore, each node has 3 degrees of freedom, meaning so 3 each, so 3, and there are 6 nodes here, 6 free nodes here, 18 degrees of freedom in this system, assuming that the foundation level nodes are completely tight, so they cannot have 18 degrees of freedom. We can make it slightly simpler. As I said, in a lot of systems, we have floor rigidity. Therefore, the lateral deflection of these 3 nodes is the same, it's U1, and the lateral deflection of these 3 nodes is the same U2. And because of, again, axial rigidity, the columns are almost rigid as well for axial movement. There's no vertical movement of interest, therefore they are not there. Now we have 2 lateral movements which are independent, really independent, and 6 rotational movements which are independent, total of 8. So going down from 18 to 8, that's a benefit in calculation or computer time, computational time, whether by hand or by software. Now, what is the difference here when we are dealing with a dynamic problem? Sometimes we can reduce number of degrees of freedom of the system. Going back here, so in the right side, we showed why we have only 2 displacement or deflection degrees of freedom. But the mass of the system is only like moving with U1 and U2. There is minor, negligible rotational dynamic effects. Maybe you guys can correctly argue that if this node is rotating, it's rotating some mass with itself, but that's pretty minor. Like, really, we don't have a major rotational movement of the masses. Sorry, I received this warning that my internet is not perfect. Hopefully it's not affecting the recording, etc. But just raise your hand if there is serious issue. I don't have that issue at home, so I don't know. I should call my provider or vendor, internet vendor. If there is a serious issue, I can switch to my cell phone. Anyways, I'm moving forward. So I'm saying that the point I was trying to make was that the mass of this system doesn't really rotate. Therefore, rotational mass is not a concern. As a dynamic system, as an earthquake analysis work, we only have 2 degrees of freedom. Now you can run your time history analysis, earthquake analysis, line earthquake analysis really with 2 degrees of freedom, and you can see the benefits. However, in 2024, some of you guys might already laugh at me. Last night, I wanted to do a test on a model that we were running. And so I think it was order of like 1,000 degrees of freedom. And I was running a dynamic test, time history analysis. We have a cloud system with 24 cores, which is not a huge number. And I wanted to do some tests, some unknowns about the software, which other guys are working on it, but they were complaining that maybe some feature is not really doing what we think it does. And I got anxious. I had to test it because I'm like signing off on those reports, etc. And I made that model and I started it. I said, okay, I go back, I come back in half an hour. I came back in half an hour and I realized that number one, the analysis had finished in 10 seconds. And number two, the system sends me email when it starts and when it finishes. And it had finished so fast that the finishing email had arrived earlier in my mailbox rather than the starting email. So I know that this obsession with reducing the size of the model, maybe it's my generation, your generation is like, okay, let's run 1,000,000 degrees of freedom and a cloud server, and it will finish in 5 hours, which is okay. But even with 1 million, maybe you guys should be concerned. If my model is 10,000,000 degrees of freedom, it doesn't finish on time, maybe I should reduce it to, instead of 10 million, be innovative and reduce it to 1 million. That's probably the concern these days, rather than for when I was learning engineering, yeah, we were concerned about 8 degrees of freedom versus 2 degrees of freedom. But high level, it's important. I think it's good to know for an earthquake engineer. Moving on with the slideshow. So furthering our discussion on degrees of freedom, this system has, say, we said 8 degrees of freedom, only 2 of them is important in the dynamic analysis. We could practically go through a static condensation and just remove the degrees of freedom where we are not interested in. That's the general setup of a static condensation. You don't have mass for certain degrees of freedom, which we said were rotational degrees of freedom. And you don't have forcing function on those degrees of freedom. So why bother? We just use static condensation and reduce the degrees of freedom of the system only to the ones that have mass and forcing function. The rest will be condensed in a way. Now, yeah, as I said, maybe if you go into analysis, then in your engineering life, you will be concerned with reducing 10 million to 1 million because it's what is important now, rather than reducing 8 to 2. But the concept is there, and maybe your software already can do that without much of your attention, or you don't need to do it directly, just the software. You should be aware of that. That's the most important issue, I think, for this course. A lot of things to be aware of and have a high level knowledge of. Going back to degrees of freedom, we already, at least during examples, we looked at the flooring system, rigid flooring system. And in this flooring system, you see, if you want to naively say it's like on one story and you want to naively look at this system, you would say I have 6 nodes and it's really a 3D system. So 6 times 6, I have 36 degrees of freedom. But with the simplifying assumptions that we discussed, you really have 3 degrees of freedom. Because vertically, again, you are not too much concerned. The columns are pretty rigid for vertical movement. For horizontal movement, because the floor is very rigid, therefore, all the movement you have is dictated by lateral movement of the floor in 2 directions and and the rotational movement. So if you know this is a plan of the floor and the bottom one is the same, and basically if you know for a rigid floor diaphragm, if you know the movement of the floor in 2 directions and the rotation of the floor, then you know enough. Anyway, And you can back calculate the movement of all the columns on top of the columns and get the forces in the columns and other forces of interest. Another additional point is that the nodal mass could be calculated based on tributary area for each node. So node 1 has this tributary area, node 2 has this tributary area. This is in case, you say, okay, it's not worth it. Two simplification is not worth it. You should be, engineers should always be, their number one issue in their mind should be economy of their work. Is it more economical if I spend 5 hours reduce the degrees of freedom of the system, or I'm very fast in using ETABS and I can just define all these nodes in 20 minutes and assign nodal mass? It's maybe faster to do the second one, but be careful what is the nodal mass for each node. Back to free vibration. So we had a discussion about free vibration in 1D, and the way it was nicely, we could estimate the period of the system and the damping of the system using a free vibration. We still keep on doing that for very complex models of dams. We do a free vibration test on the model, and we get the primary period of the system, damping of the system, which is very important. And to be like, damping is important, damping ratio, because we want to follow guidelines and a state of the practice. We don't want to overdamp our system or underdamp. And the quick free vibration test will give us an estimate of the system damping, as I explained like last week. Now for multiple degree of freedom, which is say your 2-story building, the free vibration of the system has more interesting parameters to look at, interesting specifications, which is the mode shapes of the system. So basically, as we said, there are like 2 degrees of freedom, meaning that 2 deflections U1 parts, as the generally response is complex due to unmute. Okay, hopefully everything continues seamlessly. There's a certain issue with the internet today, and hopefully we didn't cut off by much. I was trying to display of free vibration. So this plot is showing the response at 3 time instances, how it initiated and how the system continues with moving. Now I'm less confident because I don't know if everything is going on okay. I think it is. Okay. Now continuing with multiple degree of freedom free vibration. The diagram here illustrates time history of modal coordinates Q1 and Q2, no damping. So for now, we are not discussing damping. And this plot shows how the two mode shapes, the first two mode shapes of the system are reacting. The two mode shapes are really harmonically reacting. We will discuss more what a mode shape is, but let's get started here that there are two mode shapes of the system and they are independently having their own harmonic movement. And the movement at U2 is derived from the movement of these two like independent vibrations. But when you just look at U2 or you can look at U1, you don't see a harmonic movement and you think that is somewhat more random than a harmonic system, what you expect from the harmonic system. But what we are trying to learn here and emphasize here is that there are two mode shapes in the system, and those two mode shapes are really vibrating in a harmonic way. And after you calculate U1 and U2 response, they appear to be less harmonic. The two bottom diagrams show the time history of nodal displacements. Nodal displacements are not simple harmonic motions, and modal coordinates, that's what we call modal coordinate, Q1 and Q2 are harmonic. Again, going back here, the system has two mode shapes because it has 2 degrees of freedom. We look at the mode shape number 1. Normally, the lower mode shape number is the most important one and has the lowest frequency and the highest period. So the mode shape number 1 is this one. You can consider this shape remaining constant and only its amplitude is changing throughout the vibration. So how the Q1 coordinate changes, it's completely harmonic. And the way Q1 affects U1 and the way it affects U2 is again harmonic. But the only part that we have here is that U1 and U2 are affected both by mode shape number 1 and by mode shape number 2. Here is mode shape number 2, which looks different, like with mode shape number 2, M1, when M1 moves in positive direction, M2 or 2M is moving in negative direction. That's mode shape number 2 for this system. Mode shape number 2 has a higher frequency. Normally in our work, higher frequency means less important. The most important mode shape is the one with the lowest frequency. That's another thing that to just keep in mind, because you will encounter this quite often, that the more important mode shape is the one with the largest period and the smallest frequency. Again, mode shape number 2 is completely harmonic, and its effects on U1 and U2 is also completely harmonic. And these two solutions, we started with the combination. So we have solution for Q1, could be done independently, its own harmonic response. Q2, mode shape number 2 has its own harmonic response. We add the effect of these two to each other to find the deflection of U2 and U1. Number 2, which is the upper one, and number 1, which is the lower one. That's the high-level issue you should know about the modal analysis in basically 2 degree of freedom system. 2 responses, which are both harmonic, and they are added to each other. Now that we kind of high level familiarize ourselves with the physical phenomena, again, we dive into the math description. So when you write the math description, we already introduced the equation of motion, but here we said we don't have no damping, so the damping term is gone, and we have no forcing function. So the forcing function is also gone. A solution for this equation could be in this way. The deflection changes in a space and also in time. We try to separate these two phenomena, like the mode shape Phi(n) shows how it changes in a space or from U1 to U2, and Qn, which we call this coordinate, indicates how it changes with time. And we can solve for Qn and prove mathematically that the change with time is harmonic. So this is basically a harmonic description. Qn is really harmonic. And it changes with time as a sine and cosine function, which is basically what we call harmonic. Then we can insert this equation back to solve for Q, to solve for phi, because we have Q, we have solved for Q, but we don't have phi yet. We insert it back. We come up with this equation, which is called eigenvalue problem. That's why a lot of software call the function where you find the mode shapes. It's also called eigenvalue problem, or sometimes we call it just eigenvalue analysis. And the goal of eigenvalue analysis is to find the mode shapes that we mentioned and the periods. So there are important dynamic characteristics of a structure. Again, reiterating the eigenvalue problem we are dealing with. And again, in math, it's proven that only you have a non-trivial solution is 0. So that's why it's a math term. Non-trivial solution means a solution which is non-zero, because like phi could be 0 and then 0 equals to 0, very trivial. You can quickly say that. So if there is no movement, then that's one solution. However, there is a second solution, which is non-trivial, and it only holds if the determinant of k minus omega to the power of 2 multiplied by m is 0. Again, the terminology for that, if you ever came across, say you are looking at the manual of your favorite code or SAP 2000, and you see it's talking about characteristic equation, that's what they mean, or frequency equation. And the program solves this equation, which gives you the important omegas. Remember that omega was the frequency of the system. That's the way the program determines the frequency, important frequency of the system. And when you have the frequency of the system, you plug it back here. Now the frequency of system is there, and you can solve for phi n, which would be your mode shape. Eigenvalue problem, eigenvalues, mode shapes are also sometimes called eigenvectors. So I thought that it's good to you guys know this so that you're not surprised when you see this terminology in SAP 2000 manual. It's all about modal analysis and finding the dynamic characteristics of the system, mode shapes, periods, etc. One more time, showing the eigenvalue problem for a system with many degrees of freedom. And the modal mass matrix is this one, just basically mode shapes sitting by each other. Spectral matrix. I did not really come across this terminology, but maybe it's from Chopra, or maybe in some books you will see that. That's just frequency to the power of 2 in diagonal, sitting diagonally in a matrix. So that's your spectral matrix. And the compact version of eigenvalue problem is this one. So that's what the computer software will solve for you to get you the phi, which is your mode shapes, and omega, which is your frequencies. I just put in here, actually not to scare you, but exactly opposite. I want you guys not to be scared when you see these equations. That's all that is to them. If you're a researcher, spend a few years and then you will be perfect with this. Otherwise, you just need to know high level. We can prove that when n equal. Okay, so what is the mode orthogonality? Mode orthogonality is also very important feature of the solutions which are based on mode shapes. Meaning that when you multiply a mode shape by a stiffness matrix and multiply by transpose of it, that would be 0. Could be mathematically proven, and the modes are orthogonal. And hence, because the modes are orthogonal, if you calculate these two matrices for any system, they will be only diagonal. And making these matrices diagonal, that's a basis for using mode orthogonality in order to reduce a system with many degrees of freedom to a much simpler system with only a few degrees of freedom, easier to solve, like changing a multiple degree of freedom system to a lot of 1 degree freedom system. I think previously I didn't set that accurately. The intention is that instead of having a system which has 20 degrees of freedom, difficult to solve, instead of that, we will have 20 systems which each one of them have 1 degree of freedom to solve. That was a huge achievement many years ago when the computer systems were slower. But even now it's important because number one, you deal like previously the market wanted you to solve a 20 degree of freedom system. Now the market or the industry wants you to solve a 1,000,000 degree of freedom system. So still you need to simplify. Whatever the computer capacity is at, the expectation is twice as much. So you always need to be aware of simplifying solutions. And number two is that when you have 21 degree of freedom system, there is a second benefit is that the important ones which are helping with finding the deflection of the system are the first few. Like you have 21 degree of freedom system, but you're only concerned with the first 5 one, and then you can even throw away 15 of them. That's even another interesting or important benefit of this type of solution. So instead of solving a 20 degrees of freedom system, you solve 5 systems which only have 1 degree of freedom, which is huge benefit. Okay, enough. I think you know some terminology about the free vibration and the solutions which are based on the modal analysis. Back to the damping of a multi-degree of freedom system. We already high level discussed the damping of a single degree freedom system as if dampers are attached to your mass. When you have multiple degree of freedom system, you can visualize each degree of freedom of the system is attached to a damper and attached to the ground. That's the physical concept behind mass proportional damping. Like each of these masses are damped by dampers. That's yeah, I mean, this is popular in our work and useful, but it's more like a math concept than real physics concept, because it's a math concept, helps with solution. Real physics, maybe question this because we never attached a multiple story building to dampers and to some rock excavation. We never do that. So this is imaginary math, imaginary solution, which is very helpful. So it's good to be aware of that. So it's not like this building in reality is attached to some excavation or sitting in an excavation. It's only a mathematical tool in a way. So, but be aware of what this mathematical tool is telling you and why it's unreal but helpful. That's the concept of math proportional damping. Physically difficult to justify. I already said that when I prepared the slideshow last year. And modal damping ratio, generally you should be aware of that. There is a modal damping ratio, which has an inverse relation with the frequency of the system for mass proportional damping. Then we have a stiffness proportional damping, which physically makes more sense because it's internal to your structure, so physically more sensible. And a stiffness proportional damping is basically this A1, and the damping of the system is directly related to the frequency. Physically more intuitive. So that's what I try to emphasize here. And a solution which has been popular in dynamics of structure for many years is using Rayleigh damping. And the Rayleigh damping is basically using a combination of the two. The first one, mass proportional damping, which is physically less sensible. The second one is the stiffness proportional damping, which is physically more intuitive and sensible. But it's consistent with experimental data, and it has been successfully been used in analysis methods and computer software for many, many years, and SAP 2000 has it implemented. It has two terms, the mass proportional part, which is reverse relation to frequency, a stiffness proportional part, which is direct relation to frequency. And basically, you can back calculate A0 and A1 to be used based on your frequency range of interest. If you have two important frequencies in your system, which you are confident that those frequencies can create a range between the smaller one, WI, and the larger one, or omega, I should call it, omega I, which is the smaller one, omega J, which is the larger one. That's your range of interest. You're confident about that. You can calculate A0 and A1, or SAP 2000 does it for you. In terms of plots, how the damping ratio changes with frequency. So we said that for mass proportional damping, it has a reverse relation with frequency. The larger the frequency, the smaller is the damping value. Mass proportional damping is actually, if your frequency of interest is omega 1, it's good for providing some damping at your higher period or lower frequency. But the stiffness proportional damping is stronger in larger frequencies. And I said that in our work, we are not really too interested in larger frequencies. So we love the stiffness proportional damping, which helps us get rid of them, damp them out. The stiffness proportional damping basically damps out the high frequency noises, which are generally important, maybe for some other studies, but they are not as important for me as a structural engineer. For structural engineers, the higher periods are important. Rayleigh damping that I just introduced combines these two, so you get, in a way, a little bit of both. You have your mass proportional damper, which is really works in your original frequency. You have your stiffness proportional damping, which really increases a lot for high frequencies, and you get rid of high frequency noises. And in order to calibrate it, you just say what is your range of frequency of interest is. Say for your system, for your high-rise building, there is a range of frequencies that you are really interested in between WI and WJ. Everything else is nonsense. The large frequencies, stiffness proportional damping will damp them out. If normally there is none, but if there is a smaller frequencies, mass proportional damping will get rid of them. Between WI and WG, you get almost slight changes, but almost non-changing damping. And to dictate that almost not changing damping, you have equation here that SAP 2000 would do that for you, or a lot of software do that for you. That's the concept for damping. Time for questions, concerns, discussions. My apologies about, I think we had a disconnection. That was very weird. My home internet is great, so I don't know what's going on, but I should investigate it. And yeah, if there was something that you didn't hear, not audible, let me know, and we can explain one more time, or general question. I know this was very high level topic, but it's necessary that you guys be really familiar with that. Not going too deep into details, but you should be aware of those damping, Rayleigh damping, multiple degree of freedom systems, mode shapes, and periods. Let me know if there are questions about this or about your submittal today. I forgot to discuss the challenge that we had with SAP 2000. So maybe I took it for granted that SAP 2000 is always available because it has been available in the previous years. And then your IT informed me that the company, I think it's called Computers and Structures, they have changed their policy and they don't provide the student versions. similar to what they used to do. And now they expect the university to buy a full version. And they accepted to buy a few full versions. I think it's important because SAP 2000 is very important software. It's good. Anybody who has shown enough interest to come into a 4th-year earthquake engineering course, he or she or they should be also interested in SAP 2000. So important that if you haven't learned that software yet, learn it now and learn the application for earthquake engineering. It's simplified and it's in a way like engineers' common sense is well embedded in this software. So use those full versions in your lab. And the one benefit is that, I mean, with the student version, there are limitations in number of nodes. So last year, the students couldn't really use it for some of the projects, which had many nodes and degrees of freedoms. Now, with the full version, I think that shouldn't be there. So you should be able to use it for a proper structure if that's what you intend to do for your project. But as I said, there's no, I mean, there are a lot of interesting things that you can do besides analysis and design of structures. So that's up to you. They mentioned that ETABS is available. Today they said ETABS is installed and ready to go. If that's your preference, you can also use ETABS in your computer lab. But I have close to no experience with ETABS. It should be very similar to SAP, but I have used it. So you have to self-educate and take advantage of the fact that it should be very similar to SAP. And yeah, so that's where we are. Generally seeing not many questions on the project, so I think it's smooth. It should be. Let's see what we will do next. We only have 5 minutes, but just a taste of what we will do on Tuesday. Now that we high level, not diving too deep, but high level, we understood the important issues and terminology in multiple degree of freedom system. We will try to use that for some examples. Really try to prove that even with hand calculation, you can find the mode shapes and periods of two-story building. So it's good to go through this, understand it. We will do that, take notes, although many of us, including myself, we only use computer software for this purpose. And SAP 2000 is a great one. But we should be able to, at least myself, sometimes I have to double check something done by other engineers, and I have to pull out these equations and double check, which is very nice. Because sometimes they just, there are typos. In a lot of forms you fill up in SAP 2000 and maybe somebody had a typo there. That's a good way to figure it out. Yeah, so we will check this 2-degree of freedom system through a few examples. We try to calculate the Rayleigh damping. Yeah, as I said, SAP 2000 will do that for you as well. Modal analysis of a 1-story building with, I think, rigid flooring system, which practically has like fewer degrees of freedom. That's also good. I think last year I tried to find examples where it's a good reference just to keep for you and even for myself when I was putting together the slideshow. So these are good reference examples, and we will discuss them on Tuesday next week. Okay, so last chance for questions. And hopefully you have enjoyed this session, learned something, you have good plans for the weekend. It's long weekend in the US, but we already have our long weekend. So yeah, let me see question. Do you have any examples from, oh, yes, yeah, I wish you had asked that sooner. Can you, yeah, email me? Yeah, I think I have received emails from you. You say I am interested in this subject, and then I will send you that subject. So that's, I want you to be dedicated. So at least see if that means let me open. Let me open right now. Yeah, maybe I can do it right now. The folder here. Boom, boom, boom. Let's not delay this presentation. I have the presentations definitely. Earthquake, grades, yes, lecture. I should apologize, but I don't have. No, I didn't keep them. Yeah, except if I accidentally find. But yeah, take it easy. It's like maybe I shouldn't admit to that, but last year for draft, it was only participation. So whoever just submitted the draft on time, I gave him 10 points. So I only want you guys to start working on it. So you send me something reasonable, you get the 10 points. And then Bernam and I will write to you how to improve it so that you get the second 10 points. So that is the first 10 point is the easiest one. Just your own words, describe what you want to do and how many hours it takes. Your best guess. It's most probably it's excellent. And if it's less than excellent, we will tell you how to change it. Okay, Aiden, is it okay with you? Okay, yeah. So yeah, let me know. I'm here if you have more questions. Otherwise, have a good weekend. And I will talk to you on Tuesday. All right, thank you. All right, bye.